Hello, everyone. Welcome to another episode of Robo Papers. Very glad today to have Mohan and Tony joining us. They are the authors from this paper called DexWild, Dexterous Human Interaction for In the Wild Robot Policies. So thank you so much for taking the time, Tony and Mohan. Maybe as a start, perhaps Mohan, you can share a little bit about yourself and then followed by Tony.
Hi everyone, I'm Mohan. I recently graduated with a master's in robotics from Carnegie Mellon University. My research has primarily been on learning from human interactions and like human videos, both internet scale and in the wild data, and how can we extract good visual representations from them. So currently I'm working as a research engineer at Skilled AI.
Cool. I'm Tony. I'm currently going into my second year as a master's student at CMU. I've been working with Deepak for about a year now, and I'm really interested in how we can take robots out of the lab. How can we get them to generalize to different environments, different objects, maybe places that they haven't seen before in the training data. And my last project was mainly focused on using humans as a way to generate data for generalization. So yeah, happy to chat more about the paper, answer any questions you guys have, tell you a bit about the funny stories that we've had as well.
Yeah, all the behind the scenes story. I'm sure there's a
Yeah.
lot. Maybe as a start,
Yeah,
you can. So maybe we can start with that.
Yeah, absolutely.
You can share screen.
So the main motivation for this is, I don't know if you guys have collected teleop data before, but if you
Yes.
have, like, there's
It's a pain.
a whole host of problems. One is obviously if you want to collect data in different places, you have to move the robot to different places usually. Moving the teleop system and the robot can be really difficult and challenging. Also, in many teleop systems, you can't actually feel whatever you're manipulating, making it really difficult to sort of get a high task completion rate, especially for more difficult tasks. So we really wanted to ask the question, like, how much robot data do you really need to train really performant robot policies that can work in all sorts of scenarios? And sort of our methodology revolves around using as little robot data as we can, and as much other data sources as we can to sort of get generalizable robot policies. So our philosophy is that we use human data for the generalization, the affordance learning, the I guess semantic understanding of what the task is, what the objects the robot policy needs to interact with. And we use the robot data only for sort of the low level control. How do you actually control the robot hand and how objects interact with the robot, and sort of combining the two to sort of leverage both the strengths of generalization and like action grounding from the robot data and learning effectively from these two data sources.
Just to double click on what Tony said, like, so in imitation learning, you have like three different levels of data sources. So you have this internet scale data, which is like actionless. And then you have like this motion capture data where the human is doing something in the scene and you have some grounded action. Then you have the robot data. So like if you look at the volume of data that's available, so like the volume kind of funnels down. So the amount of robot data, it's very hard to collect and it's also not readily available for us to train on. So in DexWild, we are trying to combine like levels 2 and 3 and get the best benefits of both. We also start with like a pre-trained representation that kind of imbibes the internet scale data as well. So yeah, we'll dive deeper as
Sounds good.
go.
Sure. So yeah, let's go into a little bit more detail. So like, yeah, how do you set this up? First of all, what do you start with pre-training wise? Is that?
I guess Mohan can talk a bit more about the
Yeah, sure. So basically we start with a pre-trained vision transformer. So this is pre-trained on like there are two different set of weights that we use. So this is from my previous project called HRP, where we learn human affordances. We distill human affordances into vision transformers. So that's one paper, and we also have another paper called Unbiased Look at Datasets. So we have a model called Soup model, which which is like an MAE pre-trained on internet scale datasets.
Yep.
It has a mixture of like all Ego 4D, Epic Kitchen,
Okay.
some robot datasets as well. So we start with that. That's our initial model, visual encoder. Then we collect human data. So in the main screen, if you see, right, like in the main picture, you have in the wild human data. So that forms majority of our data. And we have a limited amount of robot data. For example, if you take a particular task, we collect robot data in 1 or 2 scenes, but we scale up the human data in like more than like 20 different scenes. So we combine these two together, and within a batch, so per batch, we adjust the co-training ratios. We have a different amounts of robot data and human data. We combine these two and then train an imitation learning policy with it. So the like surprising thing about this paper is like just simple co-training works. Like we don't do any like fancy tricks to get this to work. The only thing is we normalize the data separately. That's it.
Okay.
So that's the pipeline basically. It's like an imitation learning pipeline with these two different data sources.
It's definitely very.
I think it would be helpful if you guys can share how the actual hardware looks like that you guys use
Yeah,
to
yeah,
do
yeah.
this human.
Tony will
Yeah.
explain that part.
Yep.
Yeah, so
He
I can
did that
talk a
that
little
thing.
bit more about this. So I think if you guys are familiar with the paper UMI,
Mhm.
that's like a huge inspiration for us. And that was, I guess, sort of a guiding factor in a lot of the design decisions that we made. So basically we wanted to create a system where we can collect data in many different places. We wanted a system that would collect high quality data so that we can use it for things like co-training directly rather than, other kinds of training like pre-training where the data quality maybe doesn't matter as much. And we wanted the system to be robot agnostic. So unlike UMI, where if you collect data with the UMI grippers, you have to deploy the policy using the same UMI grippers. We wanted, since the human hand isn't the robot hand anyways, we wanted to create a data collection system where you could use your own hand and be able to retarget that to any robot hand that you have. So the way we do this is with a very simple mocap system that we designed, which basically allows you to track your finger hand poses as well as capture wrist images that look like this, which basically allows the policy to focus more on the environment and the objects that it's manipulating rather than other things like the robot itself and other embodiment specific information. So we have 2 wrist cameras on each hand, combined with a motion capture glove, and this gives us hand tracking and wrist observations. And to actually track the wrist pose in 3D space, we use an Aruko marker. Initially, we were experimenting with similar things as UMI, like SLAM-based methods, but we found that for some tasks where your hand needs to get close to like larger objects, for example, I don't know, toaster oven or a cupboard or something, it would often lose tracking because obviously the whole vision of the SLAM is now like occluded with this big object.
Yeah, no visual features basically.
Right. Yeah.
So we ended up using this Aruko marker tracking. And to track the marker, we use this Z camera, which you can either wear on your head, or usually like we're collecting more static tasks. So it's more comfortable to just set up a temporary tripod, which doesn't require it to be in any particular position. You could just place it next to where you're collecting data and basically it would track your wrist. So then we have hand from the glove, observations from the wrist camera, and wrist tracking using the third person camera.
And so at test time, you're not using that third person camera though, right? Or are you?
Yeah. So at test time,
No.
we're only using the wrist camera observations. Since the arm itself, you can get the end effector poses directly. So we just use the wrist cameras as input to our policy, and we use some like previous actions as well. But I can go into more detail about the inputs and outputs of our policy, our architecture and stuff.
Yeah,
But
Tony, I have a few follow-up questions to this setup. Could you comment a little bit about the glove that you guys are using? What granularity, what kind of frequency can this glove that you're using to track?
yeah,
I
so
guess the
this
hands movement.
glove is from this company Manus.
Mhm.
I think it's gotten more popular throughout the years.
Mhm.
Basically, it allows you to get very high fidelity hand pose information. And the format that we get is like fingertip key points in the wrist frame, sorry. And I think they have some proprietary, I guess, tracking method for the hands, but I think it's based on EMF.
Mhm.
But it's like very lightweight, it's battery powered, it's wireless. It allows you to use the full dexterity of your hands. And I think the accuracy is around 7 millimeters, within 7 millimeters of each finger, like position in 3D. So it's fairly accurate. The benefit of using something like gloves is that uh, a lot of tasks, your hand will get occluded. Like if I pick up a bottle, for example.
It's
Mhm.
basically
Using-
self-occlusion, right? Yeah.
Yeah, so if you're using vision-based methods, you often get really jittery poses, like really inaccurate tracking. And we wanted the highest quality possible. So that's why we chose.
Yeah, that's basically the
glove.
trade-off that we took. Like if you look at our system, like the costliest part is the glove, basically. So it's like a trade-off that we took.
Mhm.
But like if vision methods improve, they can probably like replace the glove, and our system, like the pipeline, would still can easily incorporate like having a vision tracker as well.
How much is the glove?
5K.
So the glove is $6,000 for a pair if you have education pricing.
Okay.
It's not cheap, but
It's like comparable to
I-
your X arm then, right?
Yeah,
No.
yeah.
yes.
Okay.
But I think like given enough time, like the cost will come down. Like someone from, I don't know, China or someone will try to reproduce it and
Yeah.
make it much
So another
cheaper.
thing with the glove is like, because like the tracking is so reliable, like our speed of data collection is also pretty high. So if you look at these vision based like teleop systems, like a human needs to move very slowly to collect the data. Like
Mhm.
Yeah.
in our case, like they operate at like twice the speed as the robot.
Well, the tracking is from the April tag, though, right? The cube that you mount on it. So that should apply to
Like the
anything.
glove-
Or do you mean also
the
the
glove-
joint states?
Even the joint states, right? Yeah,
Gotcha.
being able to move, like grasp at a natural way that humans can.
Yeah, makes sense.
Yeah, I guess another question I have is that like what I've seen sometimes when they talk about wrist camera, the wrist camera is on top of the wrist, like looking at the upper side of the hand, and whereas I think in your case you have two that's between and then looking down. What are your consideration for that?
Yeah, Tony has a good story for that. We really
Yeah, so
Mhm.
I really I think finding wrist camera position was really challenging for us.
Mm.
Especially in the beginning, I was trying to use a GoPro like Yumi.
Mhm.
And if you ever held a GoPro, it might not seem very big, but when you're trying to attach it to your wrist, it's quite
Yeah.
You had it
quite
like under the
large.
wrist like this, or how did you?
Yeah, like
okay.
I was trying to attach it under the wrist, like
yeah.
on your forearm. But I found that I was like really uncomfortable, and the tracking accuracy was not that good anyways. So I tried to ditch the slam thing and then just put a Ruko markers. But then you also have the question like, okay, then where do you put the cameras? And I sort of started by putting just one camera on like between the index and the thumb.
Mm.
And I wanted to position it in a way that it doesn't look too much into the hand, so that like if you look at the image, like there isn't too much embodiment specific information other than maybe the thumb.
Mhm.
So like if you open your hand, for example, it basically doesn't see anything. But the problem with that is using one camera makes it really hard to judge depth. So when you're picking something up off the table, for example, it often will close the hand like very high above the object because it doesn't know the depth very well. It's not able to estimate the depth very well. And you
So
also
this
have
is like
the other
stereo camera, basically.
yeah.
Stereo
So,
camera.
this is basically a stereo camera, and the other problem is obviously if you move your hand to the left, it can't see anything to the right anymore because the field of view is wide, but it's not like that wide.
So increase your overall field of view by having to.
Yeah, so if you look at this image, for example, like it sees up to here, but like this camera can see much more. So if you would envision this hand going a little bit to the left, you can't. If you only use the left camera, you won't be able to see what's like on this side of the
specifically
table.
in this case, if you see like in the florist task, only one of the cameras is able to see the vase, right? So the left one is able to see it.
Yeah, I have a video on the website that better shows this, what the view actually looks like for the policy. And as you can see from afar, like let's say you're like sitting back, it's kind of hard to tell which one is which. That was the idea anyways. And I think for the policy, it does help a lot by aligning the visual space.
This is interesting. Why did you go with such like these are extremely distorted fisheye cameras too, not like your GoPro, right?
Yeah, so we wanted to use wrist cameras only.
Yeah.
Having a wide field of view just gives the policy much better recovery behavior because it's able to see the object even when it misses. If you have a narrower field of view and the hand moves past the object, then the object is not in frame anymore, right? Yeah, it makes it really hard to like, let's say you drop an object, but you keep going a little bit. It's like if it goes out of frame, the policy doesn't really know to go back and pick it up.
Actually, yeah.
Obviously, yeah. I think feeding in more history could help.
But it's expensive.
Yeah, it's
Yeah.
expensive.
Brain, basically.
How big is it? Okay, two questions then. How big is the model and how much history do you provide right now?
So currently,
Yeah.
Mohan, you can talk about this.
So basically, we have like we don't really have image history. So for couple of tasks we have image history, I think. But we the main thing we rely on is state history. So we found that state history is like very crucial in getting like continuous motions. So what happens is because our policies are trained to work in the wild, right, in completely unseen scenes. So if we truly only rely on the image inputs, like sometimes the policy is very hesitant. It's not very confident in moving, like doing the motion. It gets stuck a lot. So for that, like state history was very important for us. Yeah. So combining the state history along with images, was crucial.
So it's hysteresis is what you get out of the state history then. That's interesting. Okay, but the other thing that I wanted to ask before we move on to training, unless Michael has any other questions, but so you were talking about I guess maybe this is training related, but it's really camera related. So you've got these really distorted fisheye cameras. You were saying you were pre-training on these web data sets. Does that end up mattering? Like, because those don't look like the ones in Eco 4D, right? Like, or
yeah.
Right.
So that was the reason. Like, if you see, right, one thing that we noticed was, so I have this HRP paper which had very good results with ego camera viewpoint. Like the entire pre-training was done on ego camera, but like the soup from my previous work that had a mixture of everything. It had both third person, like it had ImageNet, ego 4D, robot and all that. We got like slightly better performance with soup compared to like the HRP model. We ended up using soup in the project for all our main results. So yeah, I think your question is valid. Like I think if you train only on a particular viewpoint, the problem might arise where the transfer doesn't happen. But learning a general unsupervised pre-trained representation with different data sets gives it the scene understanding. You see, right, even with this image, you have like objects in the scene, like they are positioned in certain ways. Those like high level semantics, I think, are still captured by these pre-trained representation.
Okay.
But yeah, viewpoint centric representations might not really work.
Yeah, I do want to add that we don't freeze the vision encoder when training. So
I
that
mean,
does
that's a
help a
common
lot.
thing that
Yeah.
everyone
Yeah.
does.
Do you do any ablations of like with different vision encoders, or we don't need to go down this rabbit hole if we can keep going?
Right,
But
right,
like,
right.
I'm just curious if there's any. Did you do any ablations or anything like that on this?
Yeah, we don't have in the paper, but like before like carrying out all those like hundreds of rollouts, we
Yeah.
tried to tune, and then we found like the soup worked better.
Okay. So
Slightly
like not
better.
formal, but you did test it. Yeah. Okay. Gotcha.
Yes, yes, yes.
Yeah, guys, I have a question, I guess, before we talk about trading, going back a little bit about the actual data collection part, right? I know that you guys use basically so-called non-trained, like for regular people just to collect the data.
Okay.
What
Yeah.
is the feedback from some of them? You mentioned you have problem, like even GoPro is too heavy, but after switching to your final design here, like what does that unlock, right? Can someone do this for, I don't know, like 4 or 5 hours straight? And you mentioned also something about the data mix, right? Robot learning is like 1 to 20x or something like that. So could you describe a little bit about the whole data collection process? What it's like for this data collector, I guess?
Yeah, I guess I can talk a bit about that. I think trying to scale up data collection with a bunch of untrained people, it was an interesting experience, to say the least. Like in the initial stages, like it actually helped us robustify our system a lot more. So like they basically everything that could break, like broke. Like they found different
course.
bugs, a lot of little issues with the tracking.
So basically, like first when Tony designed the system for himself, like he was saying, "Oh, it'll always work." Basically, he said, "Oh, this is always working."
Yeah.
Then he
Yeah,
gave it to the first user, and
Yeah.
he'll continue.
Yeah.
He'll continue.
You can
Yeah.
never survive first contact with real users, but but of course,
Yeah,
yeah.
so we had to like simplify a lot of the system, like make it so that they can launch it with like no coding experience, just click a button and it launches everything. Like it turns out that some people actually make a lot of mistakes while doing these tasks. So I added like a bunch of features, deleting different episodes and like resetting stuff.
I'm curious, like, why would they make more failures? Is it because they are not used to having something on their hand when they're doing the thing? What?
So the way that our data collection works is it's like task specific, right? So you have to start recording the data when you start the task and then end it when you're done with the task. It's not like sort of this play data type approach. So what some of the data collectors would do is like they would finish, but then forget to like I don't know, end the episode and then like pull out their phone and start like texting people. And later on, I added a bunch of filtering to like try to detect things like this, like abnormally long episodes and like all these like other types of heuristics. But like it's just like helpful if they can just delete if they're like, oh no, I forgot to like stop the recording. Like
Another
yeah, I had
main
to,
thing, like in terms of point of failure, is like it was hard for us to like make them understand how the robot moves as well. Like there can be certain motions of the hand that is not even feasible by the robot. So we had to train them, like show them how the robot moves and ensure that they move as closely as possible to that. Like there's certain wrist motions that the robot can't even do. So like
yeah.
if they do such motions, then those data have to be discarded.
How did you
So
give them
there's another
feedback
point
on
of
how
view.
good the data was? You could detect things like that?
Yes.
Yeah,
Yes.
so like we have a bunch of heuristics, like how quickly they're moving during the episode, how long the episodes are. Like if you move very fast, like the April tags become blurry, so it actually loses tracking. I mean, you would have to move like very fast because the frame rate of the camera is pretty high. But like we find that like over time, people sometimes get really lazy and just like start doing things super quickly just to try get as many episodes as possible. But we found that the data isn't actually as high quality and usable. because like they would grip the object super loosely, and we don't capture any tactile information, so that makes it challenging for us to retarget the motion. Because like as humans, we have access to many more modalities than what we're recording, like sound and touch and things like that, right? So basically, we have a bunch of heuristics in our pipeline that sort of tries to filter out these bad episodes where they move too quickly, or like their hand goes onto the table, or like they're looking at their phone, or like things like this.
Yeah, and one more point I wanted to add, like we didn't record egocentric. We would have ideally recorded egocentric view as well while doing the task. We didn't record that mainly because of the data collectors not being able to, like, if we impose the
They
restriction
move the
that
head too much.
they cannot move their head. If you see all those videos, right, they can't keep their head still whatsoever. So it was a pain in the ass for us to actually record that. That's why, like, we gave them the freedom, like, yeah, you can move your head. It
Yeah, it
increases
strikes
the
me.
data rate as well.
It strikes me as a interesting trade-off, right? If you use robot data or like teleop data, the humans are already forced to conform to
Correct.
what the robots can do.
Yeah,
Whereas in
exactly.
this case, because humans is free form, they can do so much, but now you have to teach the human to behave a
Correct.
lot more like the robot. Like if
Yeah,
you really
yeah,
put an
yeah.
egocentric camera, you cannot don't look left, look right too much.
I mean, I think the flip side to this is as robots get more and more advanced, this data can still be used because it's so free form, right?
Correct. Yeah, we
That's
don't
another
impose any
argument.
restrictions.
Yeah.
Yeah.
So let's say my hand that I train with today only has 6 degrees of freedom, but the data we're collecting, like our hands have many more degrees of freedom than that, and we're collecting all of that. So I think one of the big benefits of this is like I don't know if you guys seen like the Sharpa hand, for example, which
Yeah, very
which
impressive.
looks really very impressive. But let's say in 5 years, 10 years, there's like many more highly dexterous hands because we're using human hands and not imposing constraints. Our hope is that our data can continue to be used to train as long as you have the wrist cameras.
That's a great point.
What was your reject rate, out of curiosity? Like how much data did
It
these
depends
guys
on the
collect? You had to throw
data
out.
operator, basically.
Okay.
Yeah, we actually, some people were especially bad at following instructions. Some were very good. So,
Yeah,
but I
if
think,
yeah,
I
if
think
me
it's
and Tony
around,
collected, it would be like
yeah.
pretty high, like 95, 98,
Well,
something
not
like
reject rate, right?
No. Acceptance rate. Sorry. The reject rate would be like 1
I
or
got you.
2%.
Yeah, it would be
But like completely
3 or
untrained
4
would be higher.
episodes per like 300 to 400, I think. Yeah, so like that. 1 or 2%. Yeah.
1 or 2% reject rate total.
Yeah.
That's
But
pretty
like
low.
for an average user,
yeah, it depends. It
like
depends on the person.
Okay, for you guys, 1 or 2% reject rate. For an average
Yeah.
person, what would you say it was? I guess
Maybe 5 to 10%.
not bad. Yeah. Okay.
Yeah. Yeah, we do like. It actually got better with time. This is what I said. Like it was an interesting experience. Like I not only learned a lot about like how do we build more robust systems, but also like how do you train someone to do something like this efficiently? Like what are the things they have to like be aware of? So these are all like experiences that I don't know, like I learned through this process. Like it's as much like an engineering project, but also scaling up requires a lot of I don't know, like people management skills. Yeah, which was unexpected for me. I don't know.
Yeah,
and I'm sure these big companies are also have similar, I guess, experiences with hiring a bunch of data collectors. Maybe they're they're definitely more professional at training them than me, but yeah.
Yeah, I mean, every time you have humans in the loop, it ends up being a big part of it being the human like hardware interface problem, right? And
yeah,
so that's already one big part of the design, and then on top of that, the human needs to be trained.
right.
So yeah, but I definitely see the appeal, man. I mean, like this is a human can do it so much faster. That if you're trying to do teleop with any of these, probably at least maybe 5x the speed, the duration, or like 5x slower. I imagine at least.
Yeah, so I do have to say the amount of training is not much.
Mm.
Generally, when you tell someone to just pick things up and put it in a bin or fold some clothes, don't move too quickly, things like this, like they understand. You don't have to teach them how to use a robot and stuff like that.
And I guess what you get is also like you basically have a very mobile data collection, system,
Correct.
right? You
Yeah,
go out
so
to different scene. Yeah.
everything is battery powered. There are some wires for the cameras.
But they can easily be carried by one person. It's
Yeah.
fully portable.
I mean, we collect in like 90 something environments, so like we have brought this to a lot of places.
Yeah.
Yeah,
We've covered all nooks and corners of
yeah, yeah, exactly. Uh,
Interesting. It's like a one-man mobile data collection setup.
yeah,
Yeah,
exactly.
very cool.
How much data did you end up collecting? How many
so
episodes?
we have around 10,000 in total across all 5 tasks.
Yes.
10,000 episodes, right? So
Yes.
10,000
episode-
episodes.
Mhm.
Yeah.
Okay.
I think I have the exact numbers. Yeah, 9,200. Now we've collected more since then, but yeah, that's what we have.
Yeah, so I guess, so I guess now we're going to talk about training again, or maybe the evaluation. Yeah.
Yeah. Yeah. From a training perspective, can you go to the observations? Yeah. So basically, like we have 2 different camera images, like
Mhm.
as Tony highlighted in the hardware figure. Like we have 2 different cameras. So we have images from both the cameras, and we also have the proprioceptive input, like the arm state, as well as we have the intergripper state. This is something that we found that was very helpful for us, like the relative difference between the 2 arms, basically. So we use this, and we have a history for this proprioceptive state. So these are the inputs to the model, and output we predict end effector delta space. So those are the inputs and outputs, and we train both diffusion policy and action chunking transformer, but with VIT encoder as the main image encoder base. So that's basically the pipeline. It's yeah.
So the main benefit of having this quality of data is that after retargeting, like it's very similar to the robot data itself. So this allows us to sort of have this very simple
Oh, okay,
training
okay.
loss.
Okay, I think I should highlight this. So we do co-training, right? When you do co-training, like the action space also needs to match. Like the action dimensions that we are predicting for the hand joints, they should match between the human and the robot. So we do retargeting to match the action space of the human hand to robot hand. So this retargeting you can do for different hands. This is like hand agnostic. So the data that we collect, you can use that to co-train with any hand embodiment. So that's like one
So
of the main advantages.
we actually show some results on. So we train mostly with this hand. This is the Leap V2 Advanced, and we show that by just simply retargeting to this Leap hand, I'm sure you guys have seen before, like the policies are able to generalize just as well, just using the human data. We do have to collect a few demos on this hand, around 100, I think. 100, yeah, around 100. But in the lab, which is a good big benefit.
So the main thing is like what we noticed was like in our ablations when we ran policies which are trained only with human data, right? So they would generally move towards the object, like do the motion, but like the actual grasp part was the hardest part. Like it would not complete the grasp. It would either like try to grasp before the object, or like the object would slip off and it would not notice. So the main reason we need robot data is for that grasping part, like the final hand joint control part. Otherwise, like human policies generally move in the right direction. Like they have a good semantic understanding of where to move in the scene. So what we do is we collect robot data only in like 1 or 2 environments. It could be in the lab also. It doesn't have to be in the wild. Like human data we collect in the wild. Robot data is like in a few limited locations. So when we combine these two, yeah, we get the best of both worlds. So if you look at the plot here, so we divide the performance into like 3 different segments. So one is in-domain performance. Oh, one thing to note here is like all evaluations are done on like test objects. We don't use any train objects. So
Yeah.
they're all test objects. So in-domain performance is where you have both robot data and the human data, like scenes where we have both. So in that, like the performance difference is not that huge if you see between our method and the robot method, like just robot only data. In the wild is where the robot has not like we don't have robot data in the scene, but we have human data in the scene. So yeah, here you start to see the gap, like the performance goes up for our model, like the co-trained one. So the gray one is the robot one. So the performance drops. And in the wild extreme is where like the performance drop is the most. So all the videos that you see on our website, they're all like in the wild extreme scenes.
What is the difference between extreme and just in the wild?
Yeah. I'll come to that. So in the wild
Okay.
extreme is we don't have human data and robot data in that scene. It's like completely new scene.
Gotcha.
We just
Okay.
drove the robot around and then we evaluated and we
Roll the
got
robot somewhere and roll out the policy.
Yeah, that's it. Like just look at the scene. Oh, if it looks cool, yeah, just evaluate. Yeah.
Nice.
So that's why that's the difference between in the wild and in the wild extreme. And that's where we get the maximum benefit as well from this co-train policy.
Sorry, Mohan, can you go back to the chart again? What is the delta? So it's like going from something like, let's say, close folding or florist, literally go from nearly 0 to at least 60%, something like that.
Right.
I see.
Right.
Yeah,
Yeah.
so
Go ahead.
I guess I can sort of explain the intuition for this.
Mhm.
So what is the human data good for? It's good for understanding. It's good for approaching the object, having this general motions.
Mm.
And then the robot data is good for low-level control. So what you see is when you roll out the robot policy in the wild, it sometimes attempts to approach the object, but sometimes it doesn't even attempt to approach the object. It's just completely confused about what it's supposed to do. So sort of the human policy helps guide the robot towards the object close enough such that like it becomes more in distribute, because the closer you get to the object, the more of the object takes up the scene. And the robot has the object in the context of the robot data before.
Right.
So it becomes more in the robot distribution.
Well, it hasn't, you said, right? Like, because I thought they were all unseen objects.
Well, it's seen
It's in the
similar
class,
category.
I guess. Yeah.
Yes.
Okay. Yeah. All right. Fair enough.
So,
Yeah. Okay.
I mean, as you
Yeah,
can
at least
see,
the same
like,
action would work on object. So yeah, similar action at least.
yes. So, like, it's if it's seen other bottles before, for example,
Sure.
like
Yeah,
then
it has
knows
seen
to
models of
grasp.
different lengths. So where to grasp, like when to actually close the fingers, it has learned for different object classes.
Then it's able to execute the low-level control to actually pick up the object.
Does it know that it's on does it know it's on the robot versus a human hand? Like, is that visible from the observation?
Like the fingers are like visible.
The fingers are
like
somewhat
the fingers
visible.
are
Okay.
visible.
Yeah.
But like the co-training is able to handle this small visual gap. Like, yeah.
So I think, Mohan, I think it's maybe important to explain how the co-training per batch ratio works and how, like,
Correct. Okay.
since we
sure.
have a lot more human data than robot data, but we do
Okay,
train with a more balanced ratio.
Yeah, in order to balance the amount of robot data seen within a batch, so we empirically tried different co-training ratios. So what we mean by co-training ratio is per batch ratio between the robot and human data. We
Yeah.
tried, let's say you have 256 items in a batch, 128 will be robot and 128 human. That is 1:1. The ratio is based on a robot is to human. So we tried 1:1. Robot only is like 0 human. 1:1, 50-50. Then 1:2, 1:5. We empirically found out that like having Like one part robot data and then like 2 parts of human data really helped us. Yeah. So we had to do this. Otherwise, like if we naively just sample from the combined data set, then like the amount of robot data seen would be very less.
Yeah.
So
And you said you
we
only had
just
100 examples of human data, right, per task, or was it more than that?
Human
No,
data, we have
Robot
much
data.
more.
Robot data.
Robot, it depends on the task. Like
Okay.
this one, we have like around 111. Some of them we have a little
Okay,
bit
but it's
more.
on the order of hundreds as opposed to thousands for the human data.
Yes.
Okay. Yeah.
yeah, like from scene perspective, you can think that
Yeah.
like we collect around 50 demos every scene. It's like
Right.
2 scenes for robot versus like 20 scenes for the human, or greater
Yeah.
than 20.
I'm
Yeah.
still a little surprised that the human data success rates are so low here, because like I would have expected that like with all the kinematic retargeting it would do okay at like grasping, but so the robot data is making more of a difference than I would have expected from that. Why do you have any idea why that is?
So we don't
Yeah.
make super like
Okay.
we don't make a lot of effort to sort of tune our retargeting for
Okay.
each specific
Like
task.
every person will collect like differently, right? Like their finger lengths are all different.
Fair enough. Okay.
And also the control frequency of the hand versus human hand, how fast it moves versus the a robot hand.
Okay.
There is some
Yeah.
delay as well, like when you get the joint inputs. Like it's much like less. The delay is much less for the human hand.
Makes
yeah,
sense.
so I guess just based on this ratio and empirically, you guys found that
I see.
1 to 2 seems to work the best as
Correct.
a mix. But
Yeah.
in reality, actually, when you guys collect the human data is easily 10x, right? The amount of robots. So in effect,
Correct.
when you do 1 to 2, you're throwing away another 7 to 8 of those.
Oh
like,
no, it's not like that.
no?
It's not like that. So
Okay.
when I mean 1:2, it's like the when you do model training, right? There's something called batch where you give one batch for every
at the
training
batch
step.
level.
Yeah.
I see.
Yeah. At
Okay,
the batch
okay. I
level,
see.
this is the co-training ratio. So
got it.
it's
Okay,
not
okay,
like
okay.
we take only like 200 human demos and 100 the robot demos. It's not like that. We take the entire data set. Like we have 2 different pool, like 100 robot demos and like more than 1,000 human demos. So every time we train the model, we take like one demo from like one image from here, like one like 2 data samples from the robot file, and then we train. So we train long enough for the model to see both data sets.
To see everything in the human.
Yeah.
Okay, got it. I see. Interesting.
Yeah, that's a common confusion. Even reviewers had asked that.
Yeah. Okay, got it. Yeah. So because so that way you run enough batches, basically you always fully utilize what you collected from the human. Okay,
Yeah,
got it.
exactly.
Okay, cool. Yeah, but I mean, you're getting, I guess, like in extreme performance, you're hitting, say, 60, maybe below 70%. Where do you think if
slightly around 70%, it's like multiples of 2.
well, depending on the task, I guess, like
Well,
florist.
Yeah, on average.
Oh,
yeah.
On average, yeah. So do you think to get to, let's say, closer to 80 or 90%, is your gut feel just collecting a lot more human data will get you that, or like in conjunction, maybe also more robotic data, or like, yeah?
That's a good question.
yeah.
Is this
So
just about showing?
Go ahead.
Yeah, so I think we sort of try to do this ablation where we train with different scales of human data while keeping the robot data scale fixed. So we fix the number of robot demos and we sort of collect more and more human demos and train policies using that. And we find that like not surprisingly, it improves performance. But we haven't seen that it like plateauing yet at our scale. But we weren't able to sort of scale up everything up to the scale where maybe it would plateau. So we aren't sure, but this is very promising, I think. But to sort of get to higher levels of success rate, I think collecting human data will take you a long way. But it also depends on the sort of tasks that you're doing.
There are other modalities that also could be added. Like we'll cover it in the limitation section. tactile information is something that could help you with improving the success rate of grasps in general, right? Like there are so many near misses that happen, and also like since this is just like a fixed. Oh, we are not using the mobile component. We use the mobile component to move the robot around, but we like policies doesn't control the base. Like if you drop the object in some unrecoverable place, it's just like pure luck, right? Like so, if you pick it up in a wrong way and then like the object bounces off the table, after that, what do you do? It's like unrecoverable. So yeah, it's very hard. I think in general, feel like tabletop like manipulation without like the mobile component, it will be very hard to achieve like 100% success rate, especially in the wild.
I think it really depends on the task.
Mm-hmm.
But for these tasks, I think scaling up a lot more human data, you can definitely reach 80%, 90%.
Yeah, you can reach high percentage. I'm just saying like 100%, like very high, like this 99.99 that they expect in like other industries and stuff.
Yeah,
Sure.
I think doing some RL on top of this would help
Yeah,
you a
that's
lot
a
to
Honestly,
reach those higher.
It still bothers me that the human data success rate is so low. I would bet that just better retargeting would help you a lot with success rate overall, because otherwise they're fighting,
agree.
right? They must be like, because it's learning, it's clearly learning something wrong, like when it comes
Right.
to actually the dexterous grasping part, like, and that data clearly exists, I would imagine, right?
Yeah, so I think part of the challenge is that when you are grasping something, you have access to sort of the force information.
Yeah.
And like, if you're not grasping it very tightly, you can still grasp the object. But to the robot, if your retargeting is even a few millimeters off, the object will just slide off.
That makes sense.
And it doesn't really have any signal due to like the camera angle. It doesn't have, I mean, even with a third person camera, it's very hard to tell when the robot is making contact with the object. So I think adding tactile will help a ton in improving the human performance.
If you had one of these Manus gloves, but with tactile sensors as well.
Yeah.
Yeah, fair enough.
Yeah.
Like a reskin kind of whatever. Yeah, nice.
Yeah. So I think that's quite challenging. Yeah, especially because humans are so good at just like applying the least amount of force. When like you don't grab an object really hard when you're picking.
Yeah, one more limitation of our method is like it's like a big benefit with humans where like, when the humans do these simple tasks, you never miss almost. Like recovery behaviors are like so forced and unnatural for us to like we have to tell the human, oh, you have to miss and then try to redo it. Yeah.
Like if you're picking up a water bottle and pouring into something, like you always pour it into the thing. So you never drop the bottle.
Right.
So it's really hard to capture these failure cases.
I'm just saying that like it's I think it's great to hear that you have a lot of high confidence that like as you scale more of the human data part of it, both of you are very confident that the performance will improve still a lot more. Yeah, it just strikes me because I mean I've done a lot of teleop data collection myself. It is a pain. It is only meant for people who love pain, I think. Yeah. So, and I always like UMI and like I guess what you guys are doing. Maybe like Dex, Yumi. I think we're chatting with them in a few days' time. I think this kind of way of collecting from human, it is still unnatural to the human, but I think it's a lot more easy to train them to do that well than to tell you up, right? With a real robot, just moving around the real robot, setting it up, it's so costly. If they break the robot, oh gosh, like it's like few tens of grand down the road that you need to fix. Take 1-2 months to fix.
Yeah.
Yeah. I think it's a very, very promising way to scale data.
Yeah, definitely.
Yeah, I'm really excited about this direction, and I'm really happy that there's all these other amazing works working on similar directions.
Yeah, I was gonna say like, I mean, this is broadly speaking, like Chris and I obviously do this podcast. Like sometimes we talk to people who are showing us role models and simulation, and then other folks are doing like teleop, in the and then but then also there are folks like yourself doing this kind of human data. I think all three have very, very different trade-offs.
Correct.
But
Mhm.
I really like this one.
Yeah.
It's just
I
so
think-
intuitive, right?
Yeah, there's something interesting. Like there's this trend lately. I feel like over the last couple of years, where like there's so many work. There's other works like this is like all the really impressive results like this. I think those videos that you show are very cool. But like it comes down to just like collecting and scaling data. Like there was the Waymo thing about scaling laws for autonomous cars, and it just turns out that collecting lots of good data is all that you actually need, and that's what you guys do, right? I mean, not to diminish what you guys accomplished, but I feel like it's like it's interesting how much like it's a little disappointing as someone who's been in research for a long time. There's no like clever model architecture. There's no magical model architecture that makes it all work. It's like doing really good data collection. Very cool
I
stuff.
mean, this is like the bitter lesson, right? Like anything
Yeah.
that scales with the data.
Right.
Yeah.
Just needs,
Training.
yeah. The
Yeah.
bitter
It's only
lesson.
such
yeah.
only such
Right.
And I do believe that even if there are better algorithms, they'll still need probably enough data to train on.
Yeah,
And
absolutely.
We
yeah.
just really
Yeah.
don't have enough data right now.
Yeah, I agree. Like, we're so short on robot data, good robot data.
Yeah. Yeah.
Yeah. So one last thing I wanted to highlight is so we found that actually if you train if you collect enough robot data for like similar skills, you can just collect human data and be able to transfer over those skills. So like for example, picking up spray bottles,
Mhm.
we were able to like sort of learn new affordances by only collecting human data for picking up bottles, and like the picking up place for spray bottles is much higher than it is for a water bottle. So I think it's quite promising that like maybe if you collect enough robot data and have a strong foundation, you might not need to sort of collect even
Yeah,
more. You
there's
can
one
just
direction that we are thinking about in the lab, like as a future work, like where if you can collect robot specific affordance data, where like you have different kinds of grasps
foundation
that the
skills.
robot can do, like if it can achieve different kinds of grasps, and you take this model and then you fine tune it with human data, then you get the benefits of both. Well, you know all the low level controls properly, you get the high level movement from the human and like the functional grasping aspect as well.
Yeah.
Yeah, that's a direction that we are excited about.
Yeah, I think this is a good segue to ask our usual final questions. I guess if you guys have I mean you kind of allude to it already, but if you guys have let's say another 3 more months to work on this paper, like what would be something you would squeeze into this paper that do more of? Is it like spend more time collecting more human data or do more challenging tasks?
Yeah, so I've thought about this, and there's a few people in the lab working on, follow-up works to this.
Mhm.
But definitely adding other modalities would be huge because humans rely on all these different modalities to do these tasks.
Or like
So
put a
being able
microphone
to
and do audio tactile, that kind of thing.
capture that information and give it to the policy as well could
Mm.
potentially improve it a lot more. And then also potentially maybe not using real life robot data, maybe using simulation data. That could be a big direction. Therefore, like you don't have to collect any robot data. You can just collect human data in the real world and only use sim. And then also using like other robot data to like train your robot combined with some human dexterous hand data is another exciting direction.
That's
Maybe
like
some,
we
yeah.
discussed this robot foundation, like skill foundation model, right? Like which can do this basic grasping behavior. What if we could learn that from like different already existing robot data sets? So
Mm.
and then combine it with the human data for the task that you want to. So that's another direction that we're looking at.
Got it.
Yeah.
That means like totally different robotic hands or that's
Yeah,
what you
even
meant, right?
grippers maybe.
Yeah, yeah.
Got it. Interesting.
But there's lots of exciting directions, I think, that could stem from this. I mean, data is data, so you can do what you want with it. That's what's exciting, I guess.
Yeah, I think what strikes me about like robot data or like human data, I mean it's all like for robotics, is to your earlier point, Tony, that it, unlike let's say information on the internet, usually the decay time is very fast. Like, once a piece of information is out there on the web, like within 2-3 hours, like the utility of the data is not that useful. Whereas data, like you say, like your data set here 10 years later is still going to be useful because physics don't change, gravity is still the same, everywhere on Earth, and people can always find use case to keep using this data.
Correct.
Yeah.
Yeah, and I
All
think
right.
that's really exciting.
Yeah,
Yeah.
definitely.
No, definitely. Yeah, and I see that this way of scaling data is just a lot easier to scale. I mean, I completely agree with you when you say that teleop is just so damn hard. It's like it's a pain. It's really a pain.
Yeah.
But yeah, maybe one final question we'd like to ask, like, is there any like recent paper you guys come across that kind of like pique your interest that you want to give a shout out to, so that our people listening can also read those papers?
Okay.
Yeah.
Yeah, makes
Okay.
sense. Uh, yeah. Okay. So not a particular paper in general, but like the direction of like learning latent actions from actionless videos, from like these internet scale videos. We talked about how we use ground truth human actions, right? In DexWild. But yeah, I think my heart is still in like how can we leverage the internet scale videos better? Like the algorithmic part that Chris was alluding to earlier. So yeah, Genie paper that came out, and like there are all subsequent works on training like scalable latent action models, like Groot also they did, like NVIDIA Groot, and then Lapa came out. I think I'm very excited about that. We also have a paper from our lab that's going to come out soon, like it's under submission. Yeah,
Alright.
we are excited in that direction, like learning a scalable latent action model. It's called Vipra. It'll be out soon.
Cool. All right.
What's your
Keep an
sense
eye out.
of that? What's your sense of that kind of way of gathering data without action versus, let's say, the way you are doing it in this paper?
I mean, like, reduces the burden on it's all like reducing the burden, right, on the policy. So like if you can get latent actions from like internet scale data, the amount of human demos that might need in the downstream would considerably reduce. For example, like the model will learn basic movements like going up, and it'll also be task condition. Ideally, I'm envisioning like a task condition latent model. So, like the actions would be like going up or like rotating something. So these actions would be inherently imbibed in the model. So if you start with that model instead of like just plain MA pre-trained model, then the reliance on all downstream tasks, whether it's robot data or whether it's ground truth human action data, would be much less. So that's the selling point for this.
I think important to know is a lot of these latent action models train on actionless data, like videos.
Yeah, that's what, like,
is a huge.
I think I mentioned that, like, to re-emphasize, it's all like there's no action basically. It's just videos.
Cool. Yeah, Tony, how about you?
Yeah.
Any cool papers you wanna give a
so
shout out to?
I guess some papers I've found interesting recently are sort of this kind of unified multimodal prediction type papers. I mean, specifically in robotics, there's like the universal, I think, unified video action model from Sharan's lab, and then there's unified world model from UW from Abhishek's lab. And I think that and then obviously the sort of multi-input, multi-output sort of models have been sort of growing in popularity for a while now in the language vision community. And I think it's really interesting because it sort of makes the learning problem harder for the model. Like, it doesn't just now have to predict actions. It needs to predict all these other things. And I think potentially it's a way to sort of diversify the tasks and extract more information from the data that you have. And I think that's very exciting because, like, as we all know, like, these BCE algorithms are like notoriously inefficient. Like, you have to collect so many demos, and I just don't think they're using the information as efficiently as they could. So sort of this sort of unified prediction, unified input is really exciting to me. Maybe it could make these algorithms much more sample efficient and sort of extract more of the information from the data.
Yeah, extract more juice from whatever you currently have.
Yep. Cool. That's great.
Yeah. All right. Anyway, thanks so much for coming on, Mohan, Tony. It's been a really, really fun chat, and definitely looking forward to your next one.
All right.
All right, Chris, what have you learned?
I think this is a really cool paper that shows how you can collect lots of real world data and from humans, and how we can scale up data collection to do all kinds of dexterous tasks. So very, very cool work. What did you think?
Yeah, I mean, I'm very bullish on this type of like data collection. Maybe because I've done so much teleop data collection myself.
Yeah. Yeah.
I just fully understand the pain once you have like a real physical robot. I don't think you can ever like really totally discard robot data at like totally.
Yeah.
In fact, in that case, they do use a minimum amount, and
Yeah.
you do need that. But you can then co-train with a way more scalable source of data, which is just human, like, you know, putting off gloves and then do things so-called in the wild. And it just make the whole like diversity of like scenes and environment and objects like just so much more scalable, right? And so I do really like this way of scaling up. Yeah, and I'm glad these guys like open source everything, and so I'm sure there will be, you know, efforts from the community to try to improve on what they've already built, and then, you know, start to think about the second order of question, which is like, okay, how do we 1000x this kind of data collection? If it is really that simple to collect, then, you know, someone should take the effort to do that next step, which is the 1000x step. Really encouraging to see.
Yeah, I hope so. It's very cool. I think there's.
Well, the only one thing though is that like they do use this glove, the Manus glove, which costs like, you know, 5 to 6 grand.
Right.
But I think maybe it's ultimately a trade-off. I think there are definitely ways to kind of get like finger post, I guess is what you call it, with cheaper setup. Maybe still computer vision, but you make do with some occlusion and then you make some guesses.
I
Especially
definitely think if you could get force and tactile, I think things would be substantially better too.
For sure.
Like there's lots of stuff. There's lots of cool stuff to build on in this direction. But I think, yeah, definitely these kinds of tools that make data collection much easier and more scalable definitely seem to be a part of the solution for just like scaling robot data, because we just can't collect that much robot data, right? Like it's hard.
I mean, the robot is so damn expensive and they break all the time. Especially if you let it like evaluate a really bad policy and then it starts doing crazy stuff and destroying itself, you know. And then it's like at least 1 month down to do repairs and maintenance. Whereas humans are just so good at all these various things.
Yeah.
On the touch and part, I do think I don't know how you think about like audio as a way to.
I mean, I think audio is nice for this kind of stuff. There's a bunch of work using simple audio sensors for touch. Like I also just think like if it was a more like articulated glove, you could probably get something out of it from just the. I don't know. I feel like there's a lot of choices you could make to try to build a tool. Yeah. Right.
Yeah, I guess it's again another, I guess, hardware cost / performance trade-off, right? So microphone can be dirt cheap, right? You know, so are cameras these days. So if you are okay with the performance trade-off, you get really cheap hardware, then you can really lean into this whole idea that any humans can do this, and you can totally cross-source this to thousands of people around the world. Because maybe this glove is no longer $5,000-6,000. Maybe it's just cameras and maybe a couple of microphones, and that's it. And this could be So I'm very really bullish about this line of like data collection, and it's good to see researchers like pushing on this front as well.
Definitely.
Yeah. All right. Cool. I guess until the next time.
Yeah. See you next time.
All right. Okay.